Calculus, video 33, some examples of implicit differentiation. So in the last video we learned that if we're taking the derivative of a term with x's, like 3x to the fourth, take the derivative just like normal, in this case power rule, bring the 4 down times 3, 12x to the third. But if you're taking the derivative of a term with a y in it, we do bring the 4 down times the 3, that's 12y to the third, times the derivative of the y, the derivative of that inside function dy dx. That's the chain rule process we're using there because y is some function of x. So I would like to use that and go through a few examples. First example here, we have the equation 4x cubed plus 5y cubed equals 6y. And so if we're looking at that, we see I have three terms that I'm looking at. This first term, 4x cubed, that is just all x's. So that's derivative like normal. The second term, 5y cubed, that is a y term. So we'll do the chain rule there, need to multiply. We'll do the derivative and then multiply it by the dy dx. Same thing here with 6y. We'll take the derivative and then multiply that by dy dx. Should look something like this. Derivative of 4x cubed is 12x squared plus the derivative of 5y cubed is 15y squared times, chain rule, dy dx, the derivative of that inside function y, is equal to the derivative of 6y is just 6, but then since that's a function y here, times dy dx. Okay, so we have the derivative implicitly, but we need to solve for dy dx, right? The derivative of y with respect to x. We're trying to solve for the dy dx. So what I like to think about is this. Every term that has a dy dx in it gets moved to the left-hand side. Every term that does not have a dy dx in it gets moved to the right-hand side. And so we see that the 12x squared does not have a dy dx, so I'm going to subtract 12x from both sides. It's going to go to the right. The 15y squared dy dx has a dy dx, stays on the left-hand side of the equal sign. And the 6 dy dx term over here to the right, that also has a dy dx. It's on the right-hand side. I want it to be on the left, so I'm going to subtract 6 dy dx. Right, so this should look like 15y squared dy dx minus 6 dy dx is equal to negative 12x squared. All terms with dy dx on the left, any term without a dy dx on the right. Now we'll factor out that dy dx term that the 15y squared dy dx and the 6 dy dx have in common. And you might be tempted to also factor out like a 3, since 15 and 6 have 3 in common. But right now I really just want to focus on factoring out the dy dx. So since both terms have a dy dx, I'm going to factor that out, leaving me with 15y squared minus 6 is equal to negative 12x squared. Okay, and then I have dy dx times 15y squared minus 6, so to get rid of that, we will divide both sides by 15y squared minus 6. Divide by 15y squared minus 6. That cancels here, leaving my left-hand side with just dy dx, which is what I wanted, is now equal to negative 12x squared over 15y squared minus 6. And now I'm going to look at this and say, can I simplify it even further? I do see that 12, 15, and 6 all divide by 3. So you could factor out a 3. That'd be negative 4x squared here. Could factor out a 3. That's 5y squared minus 2. The 3's cancel. And get a final answer here. The derivative of y with respect to x is equal to negative 4x squared over 5y squared minus 2. There we go. We have found the derivative implicitly. But let's not lose sight of what this is doing. This is allowing me to find the slope of the tangent line at any point on the original curve. That's what the derivative does. So if I go back up here, we have this curve, 4x cubed plus 5y squared equals 6y, which honestly I have no idea without thinking about it further what this might look like. It's some curve. That curve might not even be a function, right? That curve might come back on itself. It might look, more like a cube. Just really am not sure what this thing's going to look like right now. So I am just going to draw some random curve that represents this 4x cubed plus 5y squared equals 6y. What we're trying to do, what we're trying to find is the derivative is a function, or not necessarily a function, an equation, negative 4x squared over 5y squared minus 2, that will tell us the slope of the tangent line on that original curve. So for example, again, even though I don't know what the curve looks like, we can probably find a value here that would make it work. Maybe not. Kind of made it pretty tough here. Yeah, that's gonna be tricky to find x's and y's that would make all of that work. I probably should have thought about that ahead of time. Normally you can plug like a 1 into one of these. Like if y is 1, we could try that. So if y is 1, then I've got 6 on the right, and I've got 4x cubed. If y is 1, I've got 4x cubed plus 5 equals 6. 4x cubed equals 1. X to the third is 1/4. X equals the cubed root of 1/4. Okay, not great. Not a great number, but we have the cubed root of 1/4 for our x value, 1 for the y value. Okay, if that's my point, right, that satisfies this equation. What is the slope of the tangent line at that point? To do that, we would remember our point here was the cubed root of 1/4. 1. That's my x value, that's my y value. I just made those numbers up I just needed a number, right? An x and y value that was on the curve. That would make if I plug those numbers in to the x and to the y, it would make a true equation. So that means the point is on the curve. So here's a point on the curve. If I want the slope of the tangent line at that point, I would simply, for all my x values, plug in cubed root of 1/4, and for all my y values, plug in 1. Should look something like this. The slope of the tangent line is equal to -4 times the cubed root of 1/4 squared over 5 times 1 squared minus 2. That would be -4 times 1/4 to the 2/3 over 5 times 1 squared, 5 minus 2 is 3. Whatever that number that is, right? I could plug that in the calculator and see. In fact, why not? 1/4 to the power of 2/3. That's about 0.397 times -4 divided by 3 is a slope of about -0.53. So my slope here is approximately -0.53. Okay. So with this implicit differentiation, we have the derivative function, and we can find the slope of the tangent line at a particular point. Good, let's try another one. How about number 2, y cubed minus 6y squared equals y plus 3x plus 5. Go ahead and pause the video, try this one out to see how you do. Okay, so let's give it a shot. Remember that every term that has a y in it, when we take its derivative, we'll have to use the chain rule and multiply that by dy dx. So y cubed, the derivative there is 3y squared times dy dx. Now, -6y squared, bring the 2 down, so that's -12y to the first power times dy dx. Equals. The derivative of y is 1, but we still have to multiply it by dy dx. Okay, Now the 3x plus 5, that's a term, the 3x is a term with x's in it, right? The 5 is a constant, so when we do the derivative of those, we can just take the derivative normally. The derivative of 3x is 3, and the derivative of 5 is 0. You might be saying, well, why, if it's a y, do I do dy dx, and if it's an x, I don't? Okay. If you'd like, instead of, doing the same idea, the derivative of 3x would be 3 times dx dx, right? The derivative of x with respect to x. But what is dx dx? That's just 1. And so there's no point in doing dx dx because that is simply 1. We only need to do the chain rule when it's a variable that is different than the variable we are taking the derivative with respect to. Okay, so now we have a 3y squared dy dx minus 12y dy dx equals dy dx plus 3. And what I want to do is get every term with a dy dx in it to the left-hand side, any term that does not have a dy dx to the right-hand side. The only one I'm having to move here is this one. It's going to go to the left of the equal sign. So I have 3y squared dy dx minus 12y dy dx minus 1 dy dx equals a positive 3. Then I will factor out a dy dx from all the terms on the left-hand side, leaving me with 3y squared minus 12y minus 1. Right, if you take dy dx from dy dx, you get 1 equals 3. And solving for dy dx, I'll divide both sides by what is in parentheses there, 3y squared minus 12y minus 1, to get 3 over 3y squared minus 12y minus 1. That is the derivative found implicitly. Okay, let's try maybe 2 more, maybe progressing in difficulty here. How about number 3, x, y equals 10? Now that we haven't seen this yet, every term that I've given you so far has either been all x's or all y's, right? I either just had a y or I just had an x. This term has both x's and y's. And what you want to think there is you have 2 functions multiplied together, like x times e to the x. Where the x is just x, and the y is some function of x like e to the x. And if I had given you x e to the x, and I said take the derivative, what would you do? Hopefully you would do the product rule. You do the derivative of x times the e to the x, plus you leave the x and take the derivative of e to the x, right? The product rule there. That's what we want to do here. You want to picture this x times y is not really one thing. It is one term, but it's 2 functions multiplied together, where the x is acting like the f and the y is acting like the g. So we're going to do product rule here. Okay, let's try that. Now when we do product rule, anytime I take the derivative of an x, we do it just like normal. Anytime I take the derivative of a y, we have to multiply that by dy dx. However, if the g is just being brought down, right, like an f prime g, and I'm not taking the derivative of g, I don't have a dy dx next. I'm just bringing it down. I'm not taking the derivative of it. So when I do f prime g plus f g prime for the product rule, in the first part I'm taking the derivative of f. The derivative of x is 1. Now g, that's not the derivative of g, that is just g itself. G is y, so it's going to be y. I don't need a multiplied by dy dx, since I didn't actually take the derivative of the y. Plus, we're going to leave the f, that's the x term, times g prime. Okay, this is the derivative of y, which is 1 times dy dx. And again, I have the dy dx here because I'm taking the derivative of the y term. Is equal to the derivative of 10, which is 0. And we get this, we get y plus x dy dx equals 0. Solving for the dy dx, let's move the y to the right-hand side there. And I get x dy dx equals negative y. And then to solve for dy dx, divide by the x. dy dx is negative y over x. And that is the derivative function found implicitly for the equation xy equals 10. And actually, this would have been the same derivative whether this said xy equals 10 or xy equals 50 or xy equals 1. Notice that as soon as I took the derivative, the 10 went to 0, so it really did not matter what that constant was. Okay, next one. How about number 4 here? X squared y squared minus 2x equals 3y minus 7. Alright, same idea as before where I had the x times y. I've got two functions multiplied by each other, but this time they're x squared and y squared. That's still, you should look at that x squared y squared as two functions multiplied as a product rule there. Alright, so when you're looking at this here, this x squared y squared, think about that as a product rule. You have an f, you have a g. So for that particular function, when I do the derivative, I still need to do f prime g plus f g prime. We're still using our product and quotient and chain rules while doing implicit differentiation. Alright, pause the video, give this one a shot as well. Let's see how you did. I have x squared y squared, so I want the derivative of f, that is just 2x. No need for a dy dx because I took the derivative of the x function. Then I have y squared, which is going to be brought down, plus. This time I leave the x squared, and I take the derivative of y squared. Since I'm taking the derivative of the y function, we get times 2y times dy dx. All right, so all of that here is the derivative of x squared y squared. Now I have the derivative of negative 2x, which is just minus 2. Again, no need for the dy dx because this is the derivative of x, is equal to 3y, that would be 3, times the derivative of y, dy dx, and then the derivative of 7, 0. Okay, every term with a dy dx to the left, every term without a dy dx to the right. And maybe I'll simplify here, so I've got, before I move terms, 2x squared y plus, 2xy squared plus 2x squared y dy dx minus 2 equals 3 dy dx. Okay, now let's move terms. We're going to take the 3 dy dx, go that way with that one. The negative 2 go that way. This 2xy squared goes that way because the 2xy squared does not have a dy dx, so I want to put it to the right. The 3 dy dx does have that, so I put it back to the left. The negative 2, again, no dy dx, so put it to the right. And we get something that looks like this. The 2x squared y dy dx, 2x squared y dy dx, minus 3 dy dx is equal to, all right, moving these two over, I have a negative 2, so I'll add 2 to this side, make it positive 2. And on the left, I have a negative 2xy squared, so I'll have to subtract that. It becomes minus 2xy squared. Okay, now on the left-hand side, now that I have all the dy dx's over here, I can factor out a dy dx from all the terms. That leaves me with 2x squared y minus 3 is equal to 2 minus 2xy squared. And then finally dividing, dy dx is equal to 2 minus 2xy squared divided by 2x squared y minus 3. Please don't try to cancel the 2xy squared with 2x squared y, or even like the 2's and the x's and the y's, right? You can't do it, right? Because the 2xy squared is being added or subtracted with the 2 in the numerator, so you can't cancel individually. Same thing with the denominator. 2x squared y minus the 3, therefore I can't cancel the terms from just the 2x squared y. So this is it. You could factor a 2 out of the numerator, but it doesn't really help us or make us go anywhere, so this should be fine. All right, I said 4 problems, but let's give one more a go here. Try something difficult, maybe a trig function or an e to the x or something kind of hard. Let's go with maybe a trig function. How about the sine of y cubed plus x squared equals, try to figure out how hard we should make this. How about x over y? All right, let's do the derivative. Actually, pause the video, try it, see what you can get, come back, we'll do it together. Okay, so sine of y cubed. Now, when I look at sine of y cubed, I think chain rule. I have my outside function sine, my inside function y cubed. Remembering, though, that y is itself some function of x. So it's almost like a chain rule inside of a chain rule. So, again, also recognize the cubed here is on the y, not on the sine function. So my outside function is sine. The derivative of sine is cosine, and we keep whatever the inside function was, in this case, cosine y cubed. And then the chain rule says I must now take the derivative of that inside function, so times the derivative of y cubed is 3y squared. And then, because I'm taking the derivative of a y, which is simply a function of x, I must multiply that by dy dx. Good. Okay. Then plus x squared. The derivative of x squared is 2x. Done. It's an x variable. There's nothing else to it. Is equal to, we have x over y, so let's do the quotient rule. Now when I do the quotient rule, anytime I take the derivative of the denominator, I'll have to have a dy dx. So quotient rule says that the derivative of x, that's 1, times the denominator y, minus, leave the x, times the derivative of y. The derivative of y is 1 dy dx, also known as just dy dx, over y squared. Okay, I need to get all the dy dx's to one side, and most of the time that's not hard, but this dy dx on the right is a part of a larger fraction. So let's separate that larger fraction, in this case. You kind of have two options here. One option is to separate the larger fraction and put both the y over y squared and the x dy dx over y squared. That's perfectly fine. The other option is just to try and get rid of that y squared denominator and multiply every term by y squared. And actually, maybe that's easier. Maybe we go that route. So I'm going to multiply all of this by y squared to cancel out the denominator here, which means I need to multiply all of this by y squared as well. Let's try that. So on the right-hand side, the y squareds cancel. On the left-hand side, I can combine all this. I've got a cosine of y cubed, a 3y squared, a dy dx, and then this y squared on the outside that's being multiplied in, right, to both of the terms. So if I can keep that straight, that's 3. Y to the 4th from this y squared and this y squared. Cosine of y cubed, right, that y cubed is the angle, so it can't be combined with the y to the 4th out front. And then a dy dx. Okay, plus 2xy squared, that's the y squared multiplied by the 2x, is equal to, the y squared in the denominator canceled, so I just have y minus x dy dx. Okay, now I can more easily move everything that has a dy dx to the left-hand side, anything that does not to the right, and I get 3y to the 4th, cosine y cubed, dy dx, that's that first term. And on the right here, I have a minus x dy dx. I want to add that to the left-hand side as plus x dy dx equals, I have a y still on the right-hand side, just came down from that y. And then I need to minus the 2xy squared from there. Right, so that's minus the 2xy squared. Okay, good. So if you're looking at the equal sign, To the left of the equal sign, all terms have a dy dx, so we will factor out the dy dx, leaving you with 3y to the fourth cosine of y cubed plus x is equal to y minus 2xy squared. Finally, solving for dy dx, I get dy dx is equal to y minus 2xy squared divided by 3y to the fourth cosine of y cubed plus x. And you should be comfortable with these implicit differentiation derivatives being kind of messy. I mean, that's kind of a messy answer. It's tough to really tell, did I do everything right? Did I make a mistake? This is one of those types of problems where, checking your answer to see whether you did something correct is not easy at all. And the answers will, in fact, be messy at times.